So now we're going to look at how do we find points of inflection. So when we're finding points of inflection, what we need to do is we need to figure out where the second derivative is equal to 0 undefined. And then we also need to make sure the second derivative changes sign. So how we do this first is we find the second derivative. You have to find the first and then the second. Then we set the second derivative equal to 0 and find the x values. And then the third thing we're going to do is we're going to make a sign chart for f double prime. Okay, and that will help us both to figure out the concavity, where it's concave up, concave down, and the points of inflection. So what we do is we take our first derivative, which is 6x squared plus 6x minus 36, and then we take our second derivative. So we take the derivative of the derivative, which is 12x plus 6. We're going to find where that's 0. So we set that equal to 0 and solve. So we get negative 6 over 12, which is negative 1/2. Then we make our sign chart. So we draw our number line and we put our negative 1/2 on it. And that's f double prime and f. So we're looking at the relationship between the second derivative and the original function, which will help us figure out the concavity and if there's any points of inflection. So then we test points in these intervals. So we want to test one point that's less than negative 1/2 and one point that's more. So here I could put my test point such as like -2. Again, it can be anything that's less than negative 1/2. I plug it into the second derivative to figure out the sign of the second derivatives to see if it's concave up or down. So I'm going to plug this into my second derivative. I get negative 24 plus 6. Okay, I get negative 18. The number doesn't matter. I just know that this is negative. And because it's the second derivative, that means f is concave down. So they asked you, where is it concave down? You would do the sign chart. And then you would say from negative infinity to negative 1/2. So then we do a test value, some value. Again, this interval is negative infinity to negative 1/2. This interval is negative 1/2 to infinity. So some value bigger than negative 1/2, such as 0. And we're going to plug that into our second derivative. Okay, again, to this 12x plus 6. So we get positive 6. This is positive, which means it's concave up. So because this second derivative changed signs, it doesn't matter which direction, but it changed signs, this is a point of inflection. If it doesn't change signs, then it's not a point of inflection. And then if they asked us where it's concave up, we would give the interval negative 1/2 to infinity based on our sign chart, because this is where where the second derivative is positive, so it's concave up. Okay, so let's look at one more example. So let's find the points of inflection of this one. So we're going to, again, find the first derivative. Then we're going to find the second derivative. Okay, we're going to set the points of inflection. The possible point of inflection are where the second derivative is equal to 0. Okay, so I can factor out a 20x squared. And then I get x minus 3 equals 0. Right, and then I can set each term equal to 0. This does have an x, so I do need to set that equal to 0. Same with x minus 3. Okay, so I get x equals 3 if I solve this. If I divide by 20, I get x squared equals 0. Take the square root, and I get x equals 0. So these are the two possible points of inflection. And I'm just going to write my function so I still see it. Right, now we're gonna make a sign chart of the second derivative and the original function with these as my two possible points of inflection. And then we have our intervals. So we have negative infinity to 0, we have 0 to 3, and we have 3 to infinity. And our test point, we would pick a point in each interval. So we could do this interval like -1, from 0 to 3, we could do 1, and from 3 to infinity, we could do 4. Never use the endpoints. We're going to plug each of these values into the second derivative. You can do the factored form or the original, it doesn't matter. Again, to the second derivative, because we're trying to figure out the sign to determine concavity and points of inflection. So we have 20x cubed minus 60x squared. Okay, so if I plug in -1, I get, this is -1 times 20, so -20, this becomes +1, so -60, okay, so that's a -80. So this is negative and it's concave down. I'm gonna try my second test point into my second derivative of 1. So I get 20 times 1 cubed minus 60 times 1 squared. So I get 20 minus 60, which is -40. So this is negative and it's still concave down. And then I try 4. And then I get 320. So it's definitely positive, and this is concave up. Okay. So what we found is if they asked us intervals, it is concave down from -infinity to 0 and 0 to 3. And it's concave up from 3 to infinity. Now, the point of inflection, the only point of inflection is x equals 3. And if you have to find the point, then you need to find the y value because it did not change sign at 0. So that's not a point of inflection. So if I come up here and find the y value, I plug it into the original function to get the y value. So I'm going to find f of 3. Okay, so we had f of x equals x to the 5th minus 5x to the 4th. So I would plug in my x value of my point of inflection, which is 3, to get the y value. And I get -162. So my point of inflection is the x value we got was 3, and -162 is the y value. Okay, so that's how you find points of inflection. Again, you need to make sure it changes sign and the intervals of concavity.